parallel simulation of this process when we grow these kinetic core fibers and hunt for them. Right, so now let me mention that if you grow the fibers from the kinetic cores, which will be captured by centrosomal microtubules, you'll make a lot of errors, basically because you make this effective kinetic cores, effective fibers, visible from everywhere. Right? So kinetic cores are tiny, and it is hard to make this mistake. But if you start growing the fiber and hunt for this fiber, it's easy to make a mistake, bump into right fiber and bump into wrong fiber. So there are very simple estimates which show the total time you need to spend on both search and capture and correcting the mistakes. Is this function which depends on the length of this fiber you grow. And this function is such that if you grow long fibers, you make a lot of errors. If you, but then you assemble spindle fast. If you grow only tiny fibers, you don't make errors. But then you are too slow. So the cell tries to make some trade-off between those two things. And that's where I want to finish today. So this is not, of course, the end of the story because we simply don't know the end. But the point is that the cell somehow optimizes. It makes a compromise between the speed and accuracy. And we don't know yet where does it lead us. Any questions?
So I have several questions. I'll start with one if somebody else is on that. First question, are there any error correction mechanisms in the spindle assembly process? And if so, what are they and how do they function?
Right, that's a great question. Repeat. So the question was, are there error correction mechanisms and what are they? So the tiniest molecular details are not known, but there are hints from research that there are at least two error correction mechanisms. One of them is sort of tentatively a biologist called brute force mechanism. The thing is, it's very unlikely that, so you have, for example, from one pole, you have exactly one microtubule and exactly one microtubule from another pole to the same kinetic core. Normally, there are, like, let's say, 3 microtubules from one pole and one microtubule from another pole. And then they're just force 3 times greater from this pole, and by brute force, it just pulls and pulls until this microtubule snaps. So it's corrected by brute force. But sometimes, of course, it doesn't work. And then there's a biochemical correction mechanism, which is very subtle. So all of these things are elastic proteins. So if you pull from 2 different directions, you stretch some protein. Okay. And the thing is that when this protein is stretched, one of the residue which was inside of the protein getting exposed, and this residue is starting to signal biochemically that something is wrong. Okay. And then the cell dissolves everything and starts from scratch. Other questions?
I also have a few questions, so I'll ask one. First, I want to go back to the process of growing the microtubules and targeting the different chromosomes. Has there been any comparison to the densities of the chromosomes in the cells that grow the microtubules towards the chromosome as opposed to the ones that you showed recently that grow from them?
Well, there is some semi-quantitative work. All of this stuff is just like people started doing it in the last few years. So there are hundreds of microtubules from centrosomes. Nobody knows the exact number. And then in each individual fiber growing from kinetic core, there are like 20, 30 microtubules. Not sure that that's what you're asking.
No, so the idea is that the process of growing the microtubule itself is GTPI process dependent.
Right.
So it's very costly for the cell to just show
Right.
if it doesn't know that it's going to hit something. So perhaps those cells that randomly know that they will have a high concentration
So the answer for this question is easy. The cell doesn't care about energy at all as far as mitosis is concerned. As wasteful as it seems, it's about, the estimates are, it's about 0.1% of the total energy the cell spends. 99.9% spends on running chemical reactions, cell cycle, of whatever. So all these mechanical processes, strangely enough, are absolutely inconsequential to the cell in terms of energy. So that's not a consideration at all.
So as a follow-up also, I know in the first part of your talk, you did this modeling, at least you presented the modeling of the microtubule. And I really wonder, in processes like that that are ATP dependent, hydrolysis dependent, in your models, you talk nothing about this dependency. And how, for instance, does GTP concentration, how would you account?
Right, so I am just skipping this molecular level details because I want to concentrate on a big system. But sort of the short answer that either whether dimer is associated with GTP or GTP changes its conformation in a certain way, and then the binding, unbinding constants are changing. So that's the short answer. Some of those details are unraveled, some of them are unknown, but that's sort of totally different part of biophysics.
And on actually third related question with ATP binding and conformational changes, you presented, I believe you say that this was with the kinesin, that there may be active ATP, active power stroke in really lifting the leg, right? But this really conflicts with the presentation that we saw yesterday from Professor Nuchik, whereas the ATP binding sites are really in the heads, and that this coupling between the ATP hydrolysis in those heads is very important in making sure that the protein stays persistent.
What is the contradiction? I don't.
So in the sense that if ATP hydrolysis is needed to be coupled such that one leg can stay, whereas one leg having ATP can stay, whereas the other one having ATP may bind. If you need ATP hydrolysis to also lift the leg, it seems to me that you may have some problem into coordinating this two-step.
No, there's no condition. If you mean that how physically ATP gets on and off, like one binding surface is below here, ATP comes and leaves from sort of the top of your foot. But, other than that, I can go with you over details of mechanical cycle. There's no contradiction. Everything goes like a clock.
Okay, so I'll ask another question. I have time. Okay. So when you showed your very first slide, you have tons of these microtubules that are shooting out from the centromeres. Now, one of the interesting questions that I have, especially with eukaryotic cells, is, so we have an understanding of how chromosomes get segregated into daughter cells, but there are a large number of organelles within the cells that need to be duplicated and segregated as well.
Right.
Are these microtubule networks responsible for that? And has any research been done into that? And what's the state of that?
Yeah, so there are two major sort of the transport networks in the cell. One transport is going on microtubules, another on pectin. So those are very, very interestingly sort of complementary networks. In a way, sort of microtubules always go from this centrosome, which is in the center of the cell, and go radially outward. It's like you have a capital city, and then radial railways. It's like big highways from the center to the periphery. Actin filaments are much shorter and totally disorganized in angle and in space. So those are like country roads every which direction and with intersections. So normally transport of any organelle that is happening in the cell. So organelle is coated by molecular motors. And normally all kinds of motors coat the same organelle. There are motors working on microtubules, both plus and minus M directed, and motors like myosin working on actin. So for example, you want to move your organelle from the center to the periphery, but not exactly to the very, to the very periphery. You just want to scatter it. So how it works, first you activate plus-end microtubule motor, move on highway outward, but activate it for stochastically, for a random time. Then you detach and activate myosin, and you move in random direction on country road and stuff. In the end, you have everybody scattered. And changing the sequence of activating motors, you can do anything. You can gather everybody in the capital, scatter to the very boundary, scatter randomly, get all sorts of patterns.
I just have a simple question. When you do your modeling of the microtubules as it goes through search and rescue, for example, do you model the interaction like a microtubule may hit another microtubule in some of the more dense situations, and do you account for like a, for lack of a better term, a drag force or viscous force?
So that's a great question. So we don't consider interaction of microtubules simply because mostly they sort of grow in radial direction and don't bump into each other. If from two microtubules from different poles, you can estimate that it's minuscule probability. However, the big problem is that chromosomes are sort of, they have finite volume, they're big. And then microtubule bumps into the chromosome and normally it gets catastrophes and shrinks back. And this is a big headache that we have in our code. And so one of the interesting programs I didn't mention, this published work we have is in it all chromosomes are transparent. So in actual nucleus, they're of course not transparent, and they're so dense that you basically cannot capture chromosome which is at the center of the nucleus because all other chromosomes shield it from the microtubule. So what happens, you capture outside chromosomes first, drag them to the poles, you kind of start peeling the onion. Capture next one, drag them away, capture next one, drag them away. And then all of them, then this partially captured chromosome, you start hunting from another pole. So when we do some trial simulations, which are not rigorous yet, it turns out it increases your time about 100 times. And we have no clue how the cell deals with it. So that's a very interesting question. So genetic interference in the cell is a very big deal. The cell is incredibly crowded. Probably should go to the break. I'm ready to answer the question during the break.
Good morning. And we decided it would be more interesting tomorrow. After the final lecture, we're moving all of us back in front of the hotel. If you go to the end of the Lamb Beach, there's the last kiosk there, and we're going to get all there together, get a drink, and have the final discussion. Okay, so we're going to do that. So we do that tomorrow. So I think the lecture will finish around 4:30, 5 o'clock. We go there, and we hang in there and have a discussion for a couple hours, talk about science, see about the program. I think that was sort of a nice environment to finish it, and then people are free to do whatever. And if you want to sleep and do whatever on Saturday, it's up to you. Okay? Cecilia?
Okay. So, I'm going to switch back to the molecular level for the next hour or so. And I'm going to continue from what I left this morning. And what I told you this morning is that because of the minimum concentration principle that they told us about, we can quite often we can use structure-based models to at least get an overall idea of the free energy landscape of proteins, the full energy landscape of proteins. And what I would like to tell you today is, so if you want, this is just the zero-order approximation, the starting point. But clearly is not the final solution for many different reasons. For instance, there are exceptions. There are proteins for which it's not really possible to use just a structure-based model to get not even a first approximation ideas. And also because if you want to make very accurate prediction and possibly if you want to study, if you want to use this to understand the interplay between folding, dynamics, and function, we have to be able to go to a more accurate solution. If you think what I told you this morning, that there are several, a large range of length and time scale involved, if you want, this approach, this very simplified approach, can give you an idea on the longest time scale or on the largest solution, but there may be the need to zoom in shorter time scale and shorter resolution. In this case, is not enough. So how can we proceed? Assuming that we have a good starting point. If you want, this is like the ideal gas of protein folding, and then you have to use some distributive approach to get the correction. How do we get the correction? And what are the elements, what are the ingredients of this correction? So how can we do that? One way, this is what I just said, what are the most important terms to include when you want to go beyond the zero-threshold approximation? And is this strategy robust? How can we port it to different systems? So how do we do this? One possibility is to check, as I said, the usual suspects. So let's think about what we have left out, and let's try to quantify the effect of these terms one by one. And both my group and other groups have done this, and there is a great deal of information out there. And I'm going to tell you a little bit of one of these in particular. So if you think what are the names, the most important ingredients we have left out in a structure-based model, I already told you, the assumption was that the energy was not as important as the entropy, so we have to get back some information on the energy, and the information, what we have completely disregarded is the effect of non-net interactions, because it considered only, we made the assumption that there was no frustration at all. We know that proteins are minimally frustrated, but we have abused this idea and we put the frustration to zero. So we want to see the effect of the negative frustration in the first point here. Then there is the side chain, as it was mentioned this morning. Even in the entropy, we made a lot of assumptions, we made a lot of approximations, because the side chain entropy is important. And this was the last paper I did with Jose so far. And we introduced the side chain, and this is another tool that can be used if one wants to separate the effect of the side chain, the entropy of the side chain, and the entropy of this backbone. Another important effect is the fact that we put all the energies equal to 1, because we didn't want to, as I said, we didn't want to have any competition, any heterogeneity between the different contacts, but this may have a role too. And if you're interested, there is a very beautiful review by Steve Plotkin and Janeiro. There are a few papers and a very beautiful review that goes into much detail about the effect of negative heterogeneity. And it's quite electrical, but it's very good. There is also, and this is just an initial list of things one should consider. The effect of the solvent is another important term, and so on. But this is just, to give you, again, I want to show you what are the general principles, what the general idea, one procedure to define a model, and how can we define a model that can satisfy the problem one has in mind, the question one has in mind. So I'm going to tell you a little bit about one of these, that is the effect of non-negative interactions, and all the details can be found in this paper. This paper, okay, that I did with my good friend Steve Plotkin, another product of Joseph's lab, and but also, another way to do, and I'm going to tell you about, a little bit about this, but also next I'm going to tell you another approach. That is, instead of considering all the different terms as a perturbation and try to evaluate the effect in a perturbative fashion, one could start from a different point as a zero-order approximation. And this is something we've done recently to try to develop a coarse-grained model that is no-go. And here we have to use heavily the principle of minimum frustration, and I'm going to tell you how. And we can use these to reconcile here experiments. And I'm going to give a couple of examples. But before to go to that, let me describe the effect of non-negative energy. So what we do in a structure-based ball-like model, we consider only negative interaction, and that are parameterized by this, that are quantified by this parameter Q, that is the amount, is a fraction of negative interactions in a given structure. There is the unit, the energy scale is given by parameter epsilon, that is the average energy per contact, and we assume that there is a maximum M of contacts that can be formed in the negative state. So this is just, and Q can go from 0 to 1. We can introduce back some negative energy in using the random energy model kind of approach as a perturbation. So basically, if you remember what Joseph said about the random energy model, we have a distribution of energy that is Gaussian, centered around a certain value, and we call this value epsilon. We have an energy scale for the energy per contact for the non-negative energies, and then we have a maximum MA of non-negative contact. And in the limit, so we've done this both at the theoretical level and the simulation level. So at the theoretical level, we take the thermodynamic limit. The thermodynamic limit A goes from 0 to 1. Then we have to do finite size correction for finite and for finite system. But for a moment, let's ignore this and consider A going from 0 to 1 as Q. So this is the average energy, non-negative energy per contact. And then we have a variance around this energy, because you remember in the random energy model, we have a distribution of energies. And we can do this, we can mix the two things together, because we can assume that, so if we mix the two things together, what we are saying is that we have exactly what Joseph said yesterday. We have an empty state that is, we have one particular state that is much more stable than this distribution of non-negative energies. And as far as the gap between the negative energy and the average of the distribution is large with respect to the variance of the distribution, we are in good shape. We know that we can fold. So if we have a co-model, we have this energy here, and everything is downhill toward this energy. But then we introduce these distributions to compete with this negative energy. And we can do this. This makes sense. It's not too abstract, because in principle, non-negative interactions, again, thinking that what has been optimized by natural evolution is the final, folding to the final state, non-negative interaction is the leftover, and so there are many different contributions that are quite noisy, and one can always invoke the central limit theorem and assume that we have a Gaussian distribution. I guess all of you know what the central limit theorem is, right? No? So the best definition of central limit theorem in an OS given by my husband, who says that I cook in the central limit theorem because I use too many ingredients and the taste is always the same. So this is the idea. If you have whatever distribution you have and you mix together, you extract many variables from the distribution, you always end up with the Gaussian. And many doesn't have to be the Avogadro number. Many is order of 10 or more. So this is why it's a good, when you have noisy effects, like in this case a negative interaction, it's not bad to use an Gaussian distribution to see what's going on. Yes?
Can you say again what your parameter A is?
So A is the equivalent of Q, but for no negative energy. So if you have a structure, you can list all the contacts you've made, and the ones that are in common with the negative structure go to a Q, go to count in Q. The ones that are not present in the negative structure go to A. And in principle, assuming that the lowest energy configuration are the most compact in the thermodynamic limit, Q and A have the same limit, 0 and 1. For finite size systems, it's not, there are corrections, but this can be taken into account. So this is nice because we can use all the results, the theoretical results of the random energy model and treat this system at theoretical level and see what happens to the results of a perfectly final floating. So as you remember from the random energy model, you get a distribution, a density of state, omega, that scales like the energy minus the average energy. And here in the average energy, I have one contribution from the negative and one contribution from the non-negative, because that is the average energy of the system per contact, and divided twice times the coordinates. And this energy is the total energy of the system. And then I have, this is the entropy that will be given just from the probability, the random energy model probability, but also have a conformational entropy. And because the conformational entropy is what drives the structure-based model, I want to try to incorporate it to see how the two effects compete with each other. And so we did some work with Steve, so all the details are in this paper. We can try to estimate this configurational entropy as a function of Q and A. Q and A, the total, to sum together Q and A is the total number of contacts, so it's related with the compactness of the protein, and we can use results from polymer theory, polymer physics, and try to get an estimate of this quantity here as a function of the length of the protein and other parameters like the distribution of loops in the protein, that is an important quantity to estimate the entropy from point to point. So basically, again, the idea here is that I'm going to estimate the density of state using the results of the random energy model, plus try to take into account theoretically as best as possible the configurational entropy that is what drives the go-like model. And if I don't want to, as I said, I can express this entropy in terms of Q&A, and I'm going to show you the result. But even before I do that, you may remember these are the same expression. Just as I showed you for the random energy model, now the energy is shifted because there is a negative and non-negative contribution. And the only thing you have to remember is that when you have omega, the density of state, if you take the derivative of the log of omega with respect to the energy, this is 1 over the temperature, 1 over kT. Yes. And you can invert this relation and get omega, the logarithm of omega is the entropy by definition. Boltzmann entropy is k logarithm of omega, what is omega's density of state, is written here. So using this very basic stat math, you get the energy as a function of the temperature, and the entropy as a function of the temperature, and the free energy as a function of the temperature, remembering that the free energy is energy minus ds, so both energy and entropy are estimated directly, so you can get the free energy. And because everything is expressed in terms of the parameter Q area and the temperature, I get the free energy as a function of Q area and the temperature. And here is the free energy per contact. And if I can find an estimate of this configurational entropy, just for the fact that I have a chain, I have a polymer chain, and again, this would be the only entropic contribution if I didn't have the competition of the non-negative interaction, then I can try to estimate, to see what's going on in this system as a function of the different parameters. This Z here is the coordination number, basically it's how many contacts per, on average, each single residue can make. So this, as I said, this configurational entropy here can be estimated using polymer theory. If you're interested, all the details are given in this paper. And here is expressed as a function of the compactness, eta, that is the number going from 0 to 1, 0 being completely swollen, and 1 being completely compact. And you can express the compactness as a function of the average loop length, L, and the number of negative contacts for. All of these are rigorous results coming from polymer theory. So eventually, you put everything together, you get the parametric expression for the free energy, and we can try to see what's going on as a function of the different parameters. So this is the result, and we did this at theoretical level, and then we did simulations. The parameters we want to learn in the simulation, if I go back here, clearly, I want to see what happens as a function of this epsilon and this beta. I want to see what happens when I change the distance between the negative energy and the peak of the non-negative energy, and fixing the peak of the non-negative energy when I change the variance of the distribution. Both of them will have an effect, and I know that at a certain point nothing is going to work anymore, and this point is when the gap here is comparable with the variance, because at that point, as you remember, it was a point that the folding temperature is comparable to the glass temperature, and that is going to work. But even before then, I expect some strong deviation from the structure-based, the completely frustrated behavior. So if I put everything together, this is the summary of the results from this paper. So if you concentrate on the first row here, these are the results from the theory using, I think we use beta B, this variance, the parameter regulating the variance here, B, we use 0.3. And so this is what I showed here. Theoretically, I assume that I have one negative state energy, that is when all the contacts are formed. And then I have this distribution of non-negative energy, and this is the distance and the variance. And then I can use theoretically to put everything together, and I can plot the resulting free energy here as a function of Q and A. So the function of the fraction of negative contacts formed and fraction of non-negative contacts formed. And because this is in the for the finite system, A doesn't go to 1. I always have a smaller fraction of non-negative contacts than negative contacts. It's also the maximum value of A is also a function of the strength of the negative interaction, but these are details. So we have two minima. We have an unfolded minimum where there are little contacts for either negative or non-negative, but there can be some negative or non-negative contacts. It's basically random code. It's basically very swollen polymer with a few random interaction forms, doesn't matter if negative or non-negative. And then there is a barrier, so each free energy, each contour is a difference of 1 kT. So there is a saddle point in the free energy, and then there is a well-defined for the minimum where 0 non-negative content are formed and the whole negative content are formed. And we can separate the energy and entropy contribution, and you see that they are very similar, and the barrier here comes from the almost exact cancellation of the two things. Then we did the same things in simulation, and we did it for well-studied protein, SH3 domain, and changing the value of B, these parameters, from very small value, 0.5, to actually very large area. And as you see in the simulations, there is not just one empty state, because there are fluctuations around the crystal structure, the final structure, and so there is a distribution of energies around this point, and there is a distribution of non-negative energy that becomes larger and larger as I get this parameter B, because this is exactly the parameter B does. And this is taken directly from the simulation, just looking at what values of energies are populated. And we can look using, and I'll show you in a moment how, but using basic system mechanics from the simulation with the trajectories, also we discussed this morning, and we can compute an effective free energy. And this is the result. Indeed, there are these two minima, and the unfolded minimum becomes broader and broader because this state there are more and more states that can be populated, and we can break down the contribution in energy and entropy. But so this is just to show you that at least qualitatively we get the same agreement between theory and between theory and simulation, and now we can try to ask some question about this. Because why are we doing all of this? We want to see what is the effect. For instance, one effect is one thing that would have a direct effect directly on something we can measure, something can affect even experimentally, is changing this D parameter, or later the epsilon and n. How does the barrier height change? And how is the stability of the energy state change? These are questions that are worth asking, because this is something we would expect. If there is a residual frustration in protein, this is something we want to know what is the perturbation of this residual energy in the calculations that I'm ignoring. And we found something quite nice, and at the beginning seemed counterintuitive, but then it makes perfect sense. So if we go to look at the barrier height, so we have to look at the difference in free energy between the unfolded state and the saddle point. If we project everything, for instance, in the Q direction, this is in 2D, but if we project it just in one reaction coordinate, we find something that Z short, and we can measure this the energy difference between the unfolded state and the top of the barrier, and this is going to regulate, assuming that there is nothing too funny going on in the dynamics here, meaning that there are no 2D traps here, then the dynamics, the folding dynamics is going to be completely dominated by diffusion over this barrier, and then if I can estimate this barrier, delta S daga, I can write that the folding rate is equal to a 3 factor times the exponential of minus delta S daga over Kt. So I can measure directly the effect of non-negative interaction over the folding dynamics. And when we did this, this is what we find. So this is the logarithm of K over K0 being the folding rate for the unperturbed case, where B and epsilon and n are equal to 0. And so basically this is measuring the barrier. You can either measure the folding rate kinetically, doing the kinetic simulation and looking at the distribution of folding times over many, many simulations. So doing a kinetic field of the dynamic, or looking at the free energy barrier in the free energy diagram. If this is correct, if really is a diffusion over barrier, the two things should agree. And the line here, the dotted line, is the prediction from the theory, computing the barriers from using this expression. We can plug in the numbers for different values of epsilon and n and b, and we can plot the logarithm of so the difference between the effect on the barrier from the theory, and the points are the results from the simulations for different values of b, and for different b, because this is because we have a random energy model, we can produce many different distributions of these non-negative energies for the same value of B. This is why there is an error bar, because you can have different results for different realization of the noise. But the important point here is to see that as you increase B, as you increase the variance, so if you fix the figure, the plot I have here, if you fix the peak in the distribution of non-native energy, and you fix the native energy, and you start changing the width of the non-native energy distribution, what happens is that the native state will feel more and more the effect of the tail of the non-native interaction. The noise will be stronger and stronger, but the folding rate increases. So there is a speed up in the folding. And this seems weird because we perturb away from the ideal situation, and we observe that the protein folds faster. And this we observe it both theoretically and in simulation. So the beauty of having a theoretical model here is that we can look at the expressions and disentangle the different effects. And we find that it's quite easy to see that the reason is because the entropy goes down faster than the energy, because there is a term 2 here. So then the entropy goes down with B faster than the energy. And what it means is that by allowing the formation of non-native contact, you restrict the conformational space, and actually you help the folding, because you don't have to spend a lot of time in completely open configuration and effectively reduce the search. So this is a non-trivial effect, and it's quite nice because there is a very large variation in folding rate. Yes?
So you're saying we have interactions with Go model, which should make the protein misfold because it attracted them to
It attracts the protein, yeah.
And when we add energy, it makes the protein fold faster.
Yes, this is the result of this time. In the perturbative limit, so if the interactions are small, because at a certain point, so this is the prediction of the theory, just looking at the effect of the barrier. At a certain point, not only you are reducing the barrier, but you are creating traps all over. So first of all, the dynamics is not single exponential, but is activated. And then you may have other states competing too much with the native state, and eventually it slows down. There is another mechanism stepping in. But as you see, both from the theory and from the simulation, even for a value of B quite large, up to 1 meaning that you almost, this state starts to overlap with the native state, still there is quite a good agreement. And this is something that can be exploited by evolution to tune in the folding rate and speed up or slow down a given folding process, playing with non-native energy, playing with frustration. So this is some freedom that maybe frustration can help to adjust the folding rate for the given process. And the same thing we obtain if we change if we fix the width of the distribution, but just we change the peak, the position of the peak of the non-native distribution. Same thing, at the beginning, in a very large range, up to the point where Tg, for the glass temperature, starts to become too high, too close to the folding temperature, and the folding is not a good folder anymore. You have a speed up of the folding rate by using non-native interaction. And again, the point here is that the reason is because forming non-native contacts effectively reduces the conformational space, the search is restricted, and it's easier to break weak interaction that is faster to break weak interaction than to visit very large region of the conformational space. So, and this is, so from this study, the take-home message is that non-native energy frustration can help. And this is also in line with, this is one way it can help. It can help also to create competition between different states, and I'm going to talk about that later. But so one can do this kind of analysis not only for non-active energy, one can do it for energy heterogeneity, and well, I can talk about that tomorrow if you're interested, but there are other interesting effects that emerge from there. Again, tuning this folding rate faster or slower, playing with the distribution of contacts on a protein structure. But, so this is just to give you an idea, yes?
So, did you try using this method to the protein you showed us in the previous lecture?
Yeah.
How did it change the results?
It changed the partitioning between, I mentioned this morning, between the misfold, the non-productive route and the productive route. We didn't do the theoretical analysis because it was very big protein. We did the perturbative approach on the folding landscaping simulation. So we introduced the distribution of a random energy model like distribution of non-network interactions uniformly around the protein. And the folding mechanism is quite robust, but there is, so actually, I go back.
So this, when you put noise, what is that for? The diffusion factor in this area? What's the
bar. So this is the bar, the diffusion factor, and there are all the figures in the paper we speak, but the diffusion factor here remains the same. The diffusion factor until you, if the dynamics is not activated, up to the level where TF over TG becomes, the ratio TF over TG becomes not good anymore, the only effect, the main effect is on the boundary. Because the prediction are just looking at the boundary height. And you see it here because I compare the folding rate and then TF over KT. So this shows a very good arrangement. Okay. So this just give you an idea of, yes?
Cecilia, what happens if you use this approach to the native unfolded protein? All them are non-native contacts. What happens?
Well, I don't have an answer because I didn't do it, but you cannot take, you have to take a perturbative approach on the other limit, because in this case, if I want to use perturbation theory, assuming that B and epsilon are small, and I cannot do that for the naturally unfolded protein because I don't have the strong attraction to one particular state. So I suspect this is not the best theory for that. Because when you do perturbation theory, you have to know very well what's happening in the limit of perturbation going to zero. In that case, you don't know. So, so this is just to tell you that one could try to quantify the effects that have been not considered in a zero-order approximation and see how they would scale with different variable parameters in different situations. But one other possibility is to go away from the structure-based approach, to take a different realization of the minimum frustration principle, and then to compare the results, or to use the results as a new starting point. And this is what we did a few years ago, and this is the work of two of my fellow students in the group, Fire Das, already talked about the work this morning, and Cristina Mattigiani. And the results will be published years ago in the Janeiro. So, again, I'm going to use a model, a very simplified model, where I consider one bit per residue. Incidentally, here again, I'm going to use the bit centered on the carbon alpha position. This is not necessary. You can pick, for instance, would be analogous to pick the center of mass of a residue. It's convenient to take a carbon alpha because of nice geometric regularity, but it's not. What one does in the structure-based model, as one of the figures showed this morning, puts interaction among these beads, attractive interaction only if these beads are going to be close by in the next case. I don't want to do that. I want to use 20 different colors, considering the colors, each color to represent the different chemical nature of the amino acids. Like 20 because there are 20 measures. And I want to define a matrix of interaction 20 by 20 so that I can fold this protein. This is not a new idea. It's been tried many times, and if you just do this, it doesn't work. Because if you think, when I started to think about an alternative way to encode the minimization principle in a minimalist model, I really like the idea of the 20 different colors, and so me and my students started to think hard, what is that we're missing here? And it's easy to realize that if we just consider different colors, but we have only one interaction, typical interaction distance for all different pairs, we are considering a system of spheres, and the packing of spheres is very degenerate. There are too many configurations where you can pack spheres in a very compact way. So you are introducing frustration because there is competition between different compact shapes. And this is not true when you are protein, because the geometric complementarity of different amino acids is important to have folding. Proteins are very compact and they pack very nicely. So what is the best we can do rather than using spheres? Spheres are characterized by one distance. One number gives you dual geometry. To deviate from spheres, you can use a distribution of distances. And this way, if you use a distribution of distances, effectively take into account the deviation from the spherical geometry. And we cannot do that exactly, because then we would introduce all the details we want to take into account. So we do that in a mean field way, just looking at the distribution of the distances between two carbon alphas in the PDB, whenever the protein data bank, whenever two amino acids form some interaction between the regular atoms, and we use this as a distribution in our model. So in practice, this is what we do. There is a local energy term that is easy because it's just a way to encode a bond stretching and angle bending, but this is not that important. What is driving the folding is the non-local terms that take into account the interaction between all the different non-covalent pairs. And this is how it looks like. So the interaction between residues I and J is effectively center of interaction I and J that represent your residues is something in this form. Again, it's a imperfect potential for the reason I told you this morning. Although now we are using very many different forms, and I mean this is the first result. This is still a work in progress, but I'm going to show you what we have so far. And then so then this parameter epsilon gives the strength of the interaction between two different I and J, and depends on the color of the bits I and J. Depends only on if you have here, if you have I don't know, red and yellow, you have one certain value of epsilon. It doesn't matter if you have red and yellow going to be in contact in the negative state or not. Red is going to interact with this yellow, the same thread is interacting with this yellow. So it can form a non-negative interaction during the folding. And then there is this parameter delta here, that again is a function of the colors, and can be 0, 1, and this is a way just to take into account repulsive and attractive interactions. So if you plot that potential for one particular value of epsilon, when delta is equal to 0, you simply have a repulsive chord. When delta is equal to 1, you have a 10-12 attractive potential. So this way, we can take into account attractive and effective attraction and effective repulsion between different pairs of amino acids. And then these sigma parameters here, when R is equal to sigma, you have the minimum energy. So the sigma parameters is the parameter that gives you the shape of the size of the beads, the relative distance between the interaction centers. And this is what we take. So this is what we extract from the distribution, and the distribution is taken from the protein data bank. So we have something like this, and this sigma is extracted from the distribution. So we are not considering the packing of spheres anymore because this sigma is not the same all over the world. And still, so we fix the sigma from the distribution, but how do we pick epsilon and delta so that the model works, so that the domain can fall? And we want, what we know, what we can use is that the protein must still be minimally frustrated, otherwise it cannot. I mean, there are plenty of theoretical and simulation results. How can we do that in practice? So, in practice, this is a way to enforce the minimal frustration principle. So we have one particular genetic structure, let's say this one, and we can generate random structures, for instance, giving random values for these parameters and running molecular dynamics simulation and collecting the structure during the trajectory. And if the minimal frustration principle is true, the energy of this structure, if you look at here, the energy of the genetic structure must be much lower than the energy of all the alternative compass structure that you can assume, again, if you think what I just told you, because it's just noise that the different interactions form in this folded state, we can assume is this random energy model-like distribution that must be far apart from the net state. So we call these alternative compass structures decoys, and the energy of the decoys and the energy of the net structure is going to be a function of our parameters. Because of the functional form of these interactions, we concentrate just in this epsilon. If we write that the energy in the net state is lower than the energy in each of these alternative configurations, this is a linear inequality because the energy depends linearly on epsilon. So what it means, if you have a linear inequality, if you consider these in the space of the parameters, here you have 20 by you have 210 parameters. But just consider if you have just two parameters. If you have a linear inequality in a two-dimensional space, it means that a linear relationship in a two-dimensional space is just a line. And so along the line, you have that x is equal to y. On one side, x is larger than y, and the other side, x is smaller than y. So a linear inequality is satisfied by half of the space when you draw this line. So it doesn't matter if this is a 200-dimensional space, still you have an upper plane associated with each of these inequalities, and you divide the space into parts. One that is the allowed space where the parameters satisfy the minimum frustration principle, and the other one is the space of the parameter that do not satisfy the minimum frustration principle. And you can look, so if you have many different inequalities, if they are completely independent from each other, and assuming that all these decoys are different, they are independent from each other, we can draw many of these lines. For instance, in this case, we say this is the allowed space for this particular inequality here. Then we draw this other inequality, and we have that this is the allowed space. And we look at the intersection. The intersection would be the space and the parameter, the region in the parameter space that satisfy the minimal frustration principle, take into account all the alternative compass structures that are generated. And I keep generating alternative compass structures that would represent this Gaussian distribution in the random energy model. So what happens, as I said, I have to do this in a very high-dimensional space, but just I cannot plot a 200-dimensional space, so let me plot a 2-dimensional space. I write all this inequality, and I take the intersection, and if there is one value of the parameter, one set of parameters that is going to fold my model, it's to be inside. What should I take? I'll take the center, just because if I take the center, it means that it's the maximum distance between all these inequalities, so it's the maximum gap between, is the maximum possible gap between the distribution of relative energy and the negative energy. And I start doing this with a set of decoy structure, and I get a set of parameters, and then what I do, I run simulation at temperature, slowly unfolding the protein. The model is simple enough that I can very quickly run folding and folding simulation at different temperatures. And then I quench it back to see if the protein below the folding temperature is able to recover the native structures I would like to. And at the beginning, picking the parameter random and doing the search, I'm not constraining enough the parameter space, because remember, this is a 210-dimensional space, so it's very difficult to constrain from all sides a region in a 210-dimensional space. So what happens is that I do not fold back to the native state, rather I get trapped in other compact structure. And this is good because I can just add this compact structure to my list of decoys. And I keep writing, so I get another set of inequality that is going to constrain more my parameter space. And I get a new set of parameters with a new center of the parameter space. And I keep going. And there are only two possibilities. Either the region of the parameter space that satisfies the minimum manifestation principle shrinks to 0. In that case, the model is not consistent with the minimum manifestation principle, it cannot fold. And this is what would happen if you don't change the sigma. There's work done in about 20 years ago, no, 10 years ago, 1998, showing that the region shrinks to 0 if if you take one value for sigma, one value for sigma. But in our case, we can converge, meaning that if you fold back and forth, you don't visit other traps if you slowly fold and unfold. And so you can keep these parameters and proceed and see how these parameters can reproduce the folding. You can proceed and study the thermodynamics of the system. Just because there were questions this morning, just a quick comment on how, so because what I mentioned here, and I mentioned several times this morning, and there were questions on this, what